Hello and welcome to my presentation about temporal graphs. I'm Wouter Ligtenberg, and in this presentation I will talk about the research I have done on temporal graphs for the web engineering seminar group. You can also look at this presentation online at this URL. I will start this presentation with a quick recap what I've told in my previous presentation about graphs and temporal graphs and their existing techniques. I will follow up with the query evaluation part, the different evaluations and the different queries you can do on temporal graphs, and I will end this presentation with a conclusion. Graphs have been studied for centuries. You've probably seen a graph earlier as well. A graph has vertices and edges, and the vertices and edges can both have labels, as can be seen below, and a direction to give them meaning. For example, in this directed graph, you can see that A likes B. We will use this graph later in this presentation as well. When we add a time dimension to a graph, we get a temporal graph. They're also known as temporal networks or time-varying graphs. This time dimension can be added in different ways. For example, you could think of this graph as a telephone network where the time instances, like this one, indicates the times at which they had contact with each other, which had a phone call with each other. U1 had a phone call with U1 from time instance 2 to 3. In another network, like a text message network, you only have time instances. So when I send a text to someone, there's just one time instance. It doesn't have a duration. But you can send multiple text messages, which is displayed here as well. You can also display this time graph, temporal graph, in a timeline plot to show different relations, but it comes rather, it cannot be seen very well if you make your graph bigger. When reasoning about temporal graphs, it's important to keep in mind that you cannot simply use the same algorithms that you use on normal graphs. For example, the edges in a temporal graph are not transitive. As can be seen in this graph, we have a relation from A to B and a relation from B to C, but we don't have a relation from A to C because they happen in different time intervals. Because of these changes, of these differences, it's not easy to use regular graph algorithms and data structures for temporal graphs. Even things like depth first search and breadth first search, the things that are very common in graph algorithms, cannot be used, and they would have to be redefined. However, with this time dimension added in a graph, you can think of many new ways to actually query your graph. You can think of this as reachability. Are two nodes connected with each other in a certain timestamp? A shortest path, where you need the least amount of hops between nodes when we can actually make them. The fastest path, which indicates the least amount of time traveled. In a quick example, if you have this graph here, you have a node A and you want to go to G, then the fastest path is from A to B to F to G, because it only needs two time instances, that's 2 and 3. The earliest arrival path is that as well, but the least amount of hops, which is the shortest path, goes from A to F to G, even though they don't happen in the same time instance. You can also think of propagating queries, which we will talk later about this presentation. For example, where you can only make a connection from one node to another when you have already made a connection, when you have an incoming edge in that node that happened earlier in your graph. So yeah, you can think of lots of different queries with this time dimension. That's also what I have done. A couple of existing techniques, because some parts of these have already been explored into a certain extent. Time Reach is a paper that talks about reachability queries in a time frame. They look if certain nodes are connected in a certain time frame, and they use strongly connected graphs, so graphs with a lot of connections to do this efficiently. There's also another paper which is about temporal graph traversals, which redefines depth first search and breadth first search and shortest and fastest spots for temporal graphs. Temporal graphs haven't really been defined. There's not like one definition about how you should use a temporal graph. For example, some definitions use time instances as simply one time instance, some use ranges, and some use multiple ranges. And these time instances, they're pretty important to a temporal graph. If, for example, we have a different representation here, where the nodes here form a connection, so there's a connection between 2 and 4, and it happens between, in this blue line, we have here a graph from 0 to 240 minutes. And when we have in A a time instance of 60 minutes, that means that every 60 minutes it's divided in one temporal graph, we get these 4 graphs. However, some detail has been left out. For example, in A you see 2 connections from 2 to 5 and 2 to 4, but you see that they don't actually happen in the same interval. You can let this be shown by taking a smaller time instance, for example 30 minutes, and there you can see that there's actually a difference in when this happened. However, your graph gets bigger and bigger in size. Here they use different snapshots, but you can also use a temporal graph which will rapidly grow bigger the more time instances you add to it. But it becomes a lot easier to reason with time instances. For example, when you have a time instance of 2 or 4, you can quickly see if one time instance is bigger than the other. So yeah. A graph query. We have our graph. We have our graph here that we just saw, and we have a example graph query. And these A, B, C are the variables, and we want to see if there are an A, B, C where A likes B in the time instance 7, where B likes C in the time instance 7, and where A loves C in the time instance 6. We can see that this has a couple of results. One of them is, let's see, we have Pete likes Max in time instance 6 to 8, so that is also 7. Max likes Wouter in 2 to 7, which is also in 7, and Pete loves Wouter from 5 to 7, which is also in 6. So this is a possible result for A, B, and C. If these nodes could be the same, for example, if A could be the same as C, then we also have another result here. Max likes Wouter and Wouter likes Max, and Max loves himself. That means that B becomes Wouter and A and C both become Max. These are different forms of evaluating a query, and they're very important to keep in mind when actually evaluating a query. I'll get to that in a second. You can also think of different ways to evaluating, to noting a query like this. For example, you could make the time here variable, or even the edge labels variable. So, for example, you could have from a relation from A to B and B to C, and you want that relation to happen in the same interval, but it doesn't really matter in which time interval it is. When evaluating the queries, we consider 3 different query evaluation. The isomorphism, which is an injective mapping from the nodes of the query graph, that's this graph, to the nodes of the data graph, which is this one. Since we have an injective mapping, that means that 2 nodes cannot be mapped to 1 node. We have a homomorphism, which is a mapping from nodes from the query graph to the data graph. So any node here can be mapped to any node here, but all nodes must be mapped. So they must all have a variable. They can all still be the same. And we have a simulation, and a graph simulation considers the edge preserving relations instead of the functions from one graph to another. And that basically comes down to that you can have different nodes. So we have a C here, but it can become different has different results. If we look at the query for a homomorphism, we see more results in isomorphism, but we also see that all results that are an isomorphism are also in a homomorphism evaluation. That is because they are inherited. So everything that's an isomorphism is also a homomorphism. In a simulation, we can see a lot of more query evaluations, but you can also see a relation from Max likes Wouter, and Wouter likes himself, and Wouter likes Anja. And for our query where we had A likes B, B likes C, and A loves C, the C is basically 2 different things here, because the C comes down to Wouter and Anja, which are 2 different instances. But on the plus side, a simulation is really fast to evaluate. It's running cubic time, which is a lot faster than the isomorphic and homomorph simulation. So depending on what you want in your graph here, you can choose these different query results. Then we have another query, a propagating query. And a propagating query takes into account the time instances of the edges, and that a time instance of an edge can only happen when a previous edge has been earlier. When we look at the query here, we want to know propagating query from Wouter to Hank through B, and we want this edge to happen before this edge. We see that this is possible in 2 different ways. We have Wouter, which has a connection to Anja, which has a connection to Hank, where this edge happened before this one, and one through Max. And we can also see that this edge has an earlier arrival time. So when we want to find how information propagated through the network, we can see that, well, this information came here first, so it's probably this one. These kind of queries are also especially useful for virus propagation, and seeing how does a virus propagate through a network, or where did it start, because you can also do this reverse. I want these different connections, a backwards connection where the other one came first, and then you can see where did the virus actually come from, where it originates from. These queries become a bit more complicated when you add loops in them. So when you add a loop in this query, you need to have a root node to indicate it. And when you have multiple edges coming into one node, then it would have to be strictly bigger than all of the previous edges. So for example, if I have a query which evaluates 2 incoming edges on Max, and Max has an outgoing edge to Hank, and we have 2 incoming edges here from Wouter to Max and from Pete to Max. One happens in time interval 2, the other in time interval 6, but this happens in time interval 5, so it's not a propagating evaluation. Alright, the conclusion: the research of temporal graphs is in its infancy. Regular graph methods cannot be used for temporal graphs without first modifying or redefining them. There's still a lot of research to be done in temporal graphs, but the queries that you can do are quite useful for a variety of applications. That's also for the future work, implementing different queries, because there needs to be more tests, and developing more different kind of queries. I gave a couple of examples, but you can think of many more with different complexities. All right. I thank you for listening to my presentation about pattern matching on temporal graphs. My name is Wouter Ligtenberg, and goodbye.